Okay, good afternoon, ladies and gentlemen. It's Mr. Worcester, as promised, doing a additional physics hangout. So I'd probably recommend you've got a bit of pen and paper if you want it, or just sort of sit back in your slippers and your dressing gown and enjoy. What I'm going to try and do is I'm going to try and capture the whole of P2 in an hour. And that does mean that obviously I can't go into super detail for everything, but I'll try and hit every revision topic and give you the basics, make sure you feel really confident about what you do know already, and hopefully going in tomorrow morning you take that confidence in with you. Now just before we start, you know, to give you the same tips that I give everyone before exams. Make sure you get a good night's sleep, make sure you eat some good food tonight, and in the morning you've got a belly full of food to give you the energy for your brain to work and do all those calculations tomorrow morning. Okay, so let's get started. Let's have a quick look at what I'm going to try and cover today. So P2 is split into two halves. First half is really about forces and motion. Second little bit of the first half is about energy, so kinetic energy, gravitational potential energy, momentum, Hooke's law. Second half is about electricity and a bit of radiation, and a little bit on stars right at the end. So hopefully none of that should come as a surprise to you. So probably a good place for us to start is, oh yeah, to also mention, don't forget on the wall on Frog, say hello so I don't think I'm sitting here on my own. Ask any questions if you want to ask them so I can help you out with them. Okay, a good place to start will be our equation sheet. So this is the equation sheet that's going to be given to you in the exam to give you the equations. And one of the things that it doesn't say on this is it doesn't say the units. So just going to quickly go through some of these units with you. So let's have a look at this first one. We know that forces are measured in newtons, masses are in kilograms, acceleration is meters per second squared. So you're going to have the same there, meters per second squared. Now speed is just meters per second. Okay, time is obviously measured in seconds. So if you're given units that aren't in those units, you might have to convert them to get them into the right ones. Now weight here, as we're going to look at later on, weight is a force, so that has a unit of newtons as well. Mass is measured in kilograms. Gravitational field strength is N/kg. You're most likely to get given that. I've never seen anyone ask you to work that out, but you can work out those units from the other two, because you can put them into the equation to work that out. Okay, again, force is going to be newtons. Spring constant is going to be newtons per meter, and extension in meters. Again, you'll notice that again you could work out your spring constant from the equation, knowing the other two units there. Okay, work done is a type of energy, so that's measured in joules. Force applied is measured in newtons. Distance is going to be meters again. Okay, up on this side, now everyone that I've taught will know my lovely joke of what is the power of what is the unit of power? A hilarious joke I've told you a million times. So joules and time in seconds. Okay, so anything with energy, it's always going to be joules. We've seen all those. Gravity we've seen again as well. Height is going to be in meters. So anything with energy is going to be joules. We've seen all of these ones. Now, this one might be worth spending a bit of time with. So if you do forget what the unit for momentum is, you just look at the units in the equation. So you've got kilograms, meters per second. Because it's a times, you just put all those units together, and the unit for momentum is kilogram meters per second. Okay, so you don't really have to remember it, as long as you know that the equation tells you what it is. Okay, current is in amps, charge there is in coulombs, and time in seconds. And for some reason, I'm missing the second half of the equation sheet here. So V is measured in volts. Resistance, R, is measured in ohms. The old Buddhist unit there, ohm. And what else might we want? Current in amps. I think that just about covers all of them. Okay. So onwards then, onto our forces part of the topic. So this is about balanced forces, unbalanced forces, and this idea of resultant force. So balanced and unbalanced just talks about whether the force is acting on an object of the same size or not. Now an object that's got balanced forces, where the forces are both the same size, it's either going to be not moving, or it's going to be moving at a constant speed. So its speed isn't changing if it's got balanced forces on it. So whether that be a box on a table or an object being pushed inwards from both sides or pulled outwards by both sides, if the forces are the same, its speed isn't changing, and that could be stopped or it could be constant speed. Okay, so all of these objects here have all got balanced forces on them. Now we can probably guess that the box isn't moving, that would be stationary, but this car might be moving, could have a forward force on the engine of 10 newtons and a backward force of air resistance of 10 newtons, meaning it's not speeding up or slowing down. Okay, so balanced forces mean constant speed or stationary. Okay, unbalanced forces. So unbalanced forces are going to mean that there's a kind of resultant force on this object, an overall force felt by this. We've got 100 newtons pushing it forwards and a 60 newtons, holding it back. Overall, it's going to have a forward force of 40 newtons, the difference between the two. And so the truck is going to speed up, it's going to accelerate. So unbalanced forces mean accelerating or decelerating. Okay, and resultant force, all that means is overall force. A classic question that they like to ask you is resultant force. What is the meaning of, or what's the definition of overall force? The answer being resultant force. Okay, again, just someone post on the wall for me. Let me know that my voice is coming across clearly, that I'm broadcasting properly. Just let me know up on the wall if there's any technical issues. That'd be lovely. Thank you. Okay, so acceleration, a couple of equations for this. So acceleration will happen with unbalanced forces. So let's say that in a question, we need to know how much force is being applied. So the F, how big is the F if we know the mass of the object being pushed and we know the acceleration of the object. Now that m/s is just the same as m/s squared. So that's our acceleration. So we would just plonk those into the equation. F equals m times a, 2000 times 0.05, and that will give us our answer, not forgetting to put our units on the end there. Okay, so just times those two numbers together. Okay, giving us 100 newtons at the end when you times those two together. Okay, so the car down the bottom here, this car down the bottom, what is its acceleration? Well, we've got this equation here, a equals v minus u over t. So in this equation, it tells you on the equation sheet, the v is the final speed, u is the starting speed, t is the time taken. We want to find the acceleration, which an acceleration just means the change in speed each second. So we can look at the end of the journey. This is the end of the journey over here. So it's moving at 16 meters per second. It's been going for 4 seconds. So we can just plug those into the equation. Oh, the starting speed will be over here at 0. It starts off at 0 meters per second. So you plug those into the equation, and that's going to tell us our acceleration, which should pop up here. So it's going to be 4 meters per second squared. And if you look at it, that 4 meters per second squared tells us that each second, the speed is going up by 4 meters a second. And if we look here, after 1 second, it's going 4 meters per second. After 2 seconds, 8 meters per second, 3 seconds, 12, and so on. Okay, so we can see that logically, that makes sense, that answer. Okay, distance time graphs. So distance time graph is where we plot the motion of an object, of how far away it is from the start on a graph. And let me just make sure I've got my straight line on. Okay, so this graph here, it wants us to read off the red-nosed reindeer, moves 2 meters in 3 seconds. So 3 seconds, he's moving meters. He then stops for a second. Okay, and then moves another 3 meters in 2 seconds. So that's going to be all the way up there. Now we'll see on here that we've got a few different sections. Well, the steeper section tells us that he is moving faster. So this we could say is a fast constant speed. And it is constant. It was definitely a constant speed because it's a straight line. So fast constant speed. Here we go. We've got a slower speed, again a constant speed, and then take care here that from 3 seconds to 4 seconds on this flat part of the distance time graph, he's not moved. He's stayed at 2 meters away from the start. So for that bit there, we've got stopped. Now take real care there to make sure that you're talking about a distance time graph. Looking at the axes is the most important bit there, and so that you're not confusing it with our velocity time graph. Okay, so you can look at what is the motion of the object doing at 3 seconds, what's it doing at 4 seconds? Well, it hasn't moved, the distance is the same, so it's stopped. Okay, over on the velocity time graph, so Santa's sleigh accelerated from standstill to 3 meters per second in 3 seconds. So we've got a line going up like so. He stayed at that speed for 2 seconds and then came rapidly to a stop in 1 second. Okay, so on this type of graph, on a velocity time graph, we've got accelerating for an upward line. So the speed is going up, as you can see. The speed goes from 0 all the way up to 3 and does that in 3 seconds. So that's accelerating. Now up here for this section, for this flat section, we are at 3 meters per second at the start and at the end. So that there is constant speed. Okay, so the most important bit about these types of graphs is you making sure you've read the labels there, the units on the side to make sure that you've got that bit right. So over here, the speed comes down from 3 to 0 in 1 second, so we can call that decelerating, if I can spell it properly. Okay, so the steeper the line here, the higher the acceleration. The steeper the line on a distance time graph, the higher the speed. Okay, so you might be talking about gradient. That's the steepness of the line, which is going to explain how quickly its speed is or how quickly it's accelerating on those two types of graph. Okay, you may sometimes see it for higher tiers. You may sometimes see a curved line, but again, the flatter the line on a velocity time graph, the more constant the speed. The steeper the line, the more quickly the speed is changing. So you can interpret that off of the graph. Okay, now one last thing with the velocity time graph, and this is higher tier only. So if you're asked to work out the distance under a particular part of the graph, so let's say we want the distance between 2 seconds and 4 seconds, well then it's the area under the graph. So you could work out the area of that box there. Now to do that, you can just read off the graph. So the change in time is 2 seconds from there to there, and the change in velocity is 1 to 3. So you would just do 3 times 2. You would know that the distance traveled in that time is 6 meters. And again, that's higher tier only, so don't worry about that if you're taking foundation tier. Okay, again, can I just ask someone to post a message on the wall just to make sure that that my voice is coming across okay, and that I am using this properly. Let me just refresh my wall and then I can see if anyone's posted anything. Okay, so terminal velocity and reaching top speeds. The science behind these two things are the same. So this is terminal velocity of an object falling, maybe a parachutist jumping out of a plane, or why a car or a van or a motorbike reaches a top speed. It's exactly the same science, and it's all to do with forces, okay? So we need to have a good explanation about why objects reach a terminal velocity or why objects reach a maximum speed, a top speed. Okay, so to start us off, terminal velocity is the maximum falling speed an object can reach. Now, as it's a constant speed, if it's constant, we know that the forces are balanced. And in this case, for this man jumping out of an aeroplane, the air resistance force will be exactly the same as the gravity. Okay. Next, explain why objects reach top speed. Let's have a quick look at these 3 baseballs here. So figure A shows the forces acting on the ball as soon as it's been dropped. So when something's first dropped, or a man jumps out of his aeroplane, or a car starts to accelerate from a standstill from the start line, there is only the forward force acting on it, or in this case, the downward force of gravity, or in a car, it'd be the forward force from the engine. Now, as it picks up speed, this upward force, this resistance, is going to act in the opposite direction. As it gets faster, that air resistance force is going to get bigger, until, in our diagram of C, when the object has reached its terminal speed, this backward force, this upward force, this drag force or air resistance force has increased until they're both the same size. When they're the same size, it stops speeding up because it's got a resultant force of 0. So let's have a quick look at how we can explain that in words. So let's apply it to a car. Why must all cars have a top speed? Well, the forward force from the engine starts off as bigger than the drag force. Okay, because you're just accelerating forward. If you're going slowly, you've got a low air resistance. So the car speeds up. As the car gets faster, the drag force increases until the forward force and the forward force from the engine balances the air resistance until they're the same size. when they're the same size, the car doesn't accelerate anymore because of the resultant force being 0. And resultant force, again, is just that overall force. It's basically saying that they've got balanced forces if they're a resultant force of 0. Okay. Okay, so now a little bit on work done, kinetic energy and gravitational potential energy. You'll have to excuse some of my pictures in this because I first did this when it was Christmas. So I've got some festive themed elves and I didn't have time to change the pictures. So shame it's the middle of summer when I'm doing this one. So let's have a look at work done. So the work done to, let's say, lift an object is the force that you're applying to the object times the distance you've moved it. So in this case, our little friendly elf has lifted up these marshmallow weights and they have a downward force of 2 newtons and we've lifted them up by 0.2 meters. So we can just plug these into the equation, remembering our units. Let me just go back one. Okay, so we're just plugging our numbers, 2 newtons times 0.2. Okay, and work done has a unit of joules. Okay, so now let's have a look at the work done then. How does that work done help us understand the amount of gravitational potential energy in the dumbbells there that the elf is lifting? Okay, so gravitational potential energy equals the mass times the strength of gravity times the height. Okay, so gravitational potential energy depends on how high you're lifting something. Okay, so in this case, the object has got a mass of 0.2 kilos. We're lifting it up by 0.2 meters, the strength of gravity there being 10 meters per second. So we just times all those numbers together, 0.2 times 0.2 times 10. Okay, so what we might notice is that the work done to lift the weight is exactly the same as the gravitational potential energy stored in the object. Well, it's no coincidence. It's because the work done by the little elf to lift up those dumbbells transfers into the object. So his chemical energy inside his little arms would have gone down because he's used up some glucose to lift it up. So he's done some work, and that work, as a value of energy, that work is now in the dumbbells because of their height above the earth. So work done to lift an object transfers energy into the object as gravitational potential energy. So work done is the same as the energy transferred. And this works the same with car brakes as well. Car brakes will do work to stop a car, and if they're taking away the kinetic energy of the car, that will kinetic energy in the car as it's moving quickly will turn into the work done by the brakes, so that the number will be the same. Okay, so in this case, he has dropped his dumbbells, and the gravitational potential energy at the top will turn into the kinetic energy at the bottom. Okay, and the kinetic energy of this falling object is the same as the gravitational potential energy at the top. That's because, again, the transfer of energy, all the gravitational potential energy at the top has turned into the kinetic energy at the bottom as it falls. So there's been a transfer of energy as it's fallen down. Now, I'm just going to say no one appears to have posted on the wall. So again, if I could ask a friendly person just to post on there just to show that that this broadcast is working, that would be helpful. Thank you. Okay, so transfers of energy then. I think we're all quite comfortable applying those equations. Top set pupils, you may be asked to rearrange that. So just to remind you that if we were asked to work out V, we would be looking at an equation that looks a bit like 2ke over m. Okay, so we would times both sides by 2. We would divide both sides by m, and we take the square root of both sides. Okay, just remember to do the same to both sides. Okay, so looking at Hooke's law and springs and elastics. So if we've got something that's stretchy, as long as it hasn't gone past its elastic limit, it is the as long as it hasn't gone past the elastic limit, every time I double the force on a spring, it will double the extension of it. Okay, so what we need to do is make sure that we know how to measure extension. Extension is found by the final length, so the stretched elastic, take away the start length, And they quite like asking you questions about making sure you can measure the extension, so they might show you a picture of that. Okay, so Hooke's law says if I pull on a spring twice as hard, the spring will extend twice as much. The same happens again with if I pull on it 3 times as hard, it's going to extend 3 times as much. Okay, now another way of saying that is that the force is directly proportional to the spring. Okay, now when we see a graph of this, we see a graph. Sorry, the equation for Hooke's law is force equals spring constant times the extension there. Now, when we see a graph of this, you're going to see a straight line. That's how we know it's directly proportional. And most importantly, it also goes through the origin. Now, if it doesn't go through the origin, and they've got a line up here, there's a good chance that they are actually measuring the full length of the spring. Because, of course, when there is no force on the spring, it hasn't got any extension because it needs to be just the original length. Okay, so this idea of directly proportional. Now, possible 6-mark question could be writing out a method to work out this, to plot maybe a graph of extension against force. So a possible method would be to, record the original length of the spring, add masses, maybe 100-gram masses at a time, recording the extension each time, plotting a graph of extension against force, and mentioning that the spring can't go past its elastic limit. Making sure that if that was a 6-marker, that you talk about the independent variable of your masses that you're adding, the dependent variable of the extension, control variable could be using the same spring each time. Now, should the spring overextend, you're going to see a line that's going to start to curve upwards. Now, what they'd like to ask you is to identify the point where it stops obeying Hooke's law, or stops being directly proportional, or the point where the spring has gone past its elastic limit, and that'll be there. That'll be just where the line starts to curve. That would be the elastic limit there. Okay, so there again we have our units of Hooke's law there of the components there. Okay, so a little bit of crash mats and momentum. So I've already gone through all of the units here, and I've also shown you how to just measure just to work out the units there from units of mass, which is kilograms, and velocity, which is meters per second. Okay, so over here we've got the equation P equals m times v. So calculating the momentum of the object, it's really just its speed times its mass. Now this explains why, if you were to get hit by either the bus or the bicycle, it's going to be a lot nicer to be hit by the bicycle because the mass is so much smaller that the overall momentum that's going to be transferred into you will be much less. So larger the object, the bigger the momentum. Okay, so explosions and collisions then, and this idea of the conservation of momentum. So that the law of conservation of momentum simply states that the total momentum of 2 objects before an event is the same as the total momentum of 2 objects after the event. Okay, so this applies to things which are splitting apart, like the cannon, or it applies to objects which are colliding, like the 2 cars here. So the total momentum of the cannonball and the cannon, and let's say that the cannonball is in there, that the total momentum of the 2 things before is the same as the total momentum of the 2 things afterwards. Now, for this case here with the cannon, the total momentum before, because neither of them are moving, the total momentum must be 0 of the whole system. And that also tells you that after the event, they must also be have a total momentum of 0. Now that tells us that because momentum has a direction as well, that the momentum of the cannonball must be the same as the momentum of the cannon. Okay, so that helps us to understand that the cannon has to move backwards a little bit, and the cannonball has to move forwards a little bit. Now, because of the difference in masses, that the cannonball is going to be moving much, much faster. V will be much higher because mass is much smaller. Okay, the cannon will move backwards a little bit, but not by as much because it is much heavier. Okay, with the two cars here, now if they crash into each other and they both stop dead, okay, it tells you that the total momentum after is 0, which tells us that the two momentums of the two cars must have been the same beforehand. They're just traveling in opposite directions. So that the total momentum of the two cars must be the same again. So you've got your white car going that way. The mass times velocity must be the same as the mass times velocity of that car as well. Now, most of what I've just done there mostly is higher tier. You know, you might get asked in foundation tier to calculate momentum for maybe one object if they tell you the mass and the velocity. Okay, so how can we use this idea of momentum to explain how things keep us safe? Now, in a car accident, there are 3 main features of a car that you need to be able to explain: airbags, seat belts, and I apologise for my Christmas theme again, seat belt across centre, and a crumple zone at the front. Okay, so how do each of these things keep us safe in a collision? And the science is exactly the same for each one. Okay, each one, because they change shape, so you may not know it, but seatbelts are slightly stretchy. An airbag will get smaller when your face hits it. The front of the car will change shape when the car hits the lamppost. All of them increase the time taken to stop. It means you slow down over a longer period of time. You increase your time taken to stop. Now, what does that do? That reduces the forces on the passenger or the driver. Okay, now exactly the same science works in crash mats as well. So anything, in fact, that protects you from injury. So it could be a bicycle helmet, it could be a crash mat in a gym, it could be a kind of squidgy floor in a playground. So no matter what the safety device is, if it squishes, if it changes shape when you hit it, it's increasing the time taken to stop. It reduces the forces on the passenger. And those are the two ways you need to explain how they keep you safe. Now, should you want to, if you're high there, you may want to talk about it reduces the rate of change of momentum. But you have to be sure that you're going to use every single word in there, otherwise it doesn't make sense. So it reduces the rate, how quickly the change of momentum occurs. Okay, you do not want a high rate of change of momentum because that means you're stopping quickly. You want a small rate of change of momentum to stop slowly. But foundation tier, stick to your increasing time taken to stop, reducing forces on passenger. Okay, that really is the first of the lot of the first half of P2. So again, post any questions if you're not sure of anything. Thank you for the comments. I can see now it is working. That's all good. I've realised I had to click on the button to see all posts. Okay, cool. So the broadcast is working. Okay, so static electricity then. How do we create static charge on an object? Static electricity is what sticks those balloons to the wall when you've rubbed them on your hair. So all this does is it scrapes electrons from one insulating material and transfers them to another insulating material. Has to be insulating. Doesn't work with metals, of course, because the electrons can't stand still in a metal. They travel, they're free to move in a metal. So it has to be an insulating material, and it's friction that causes the movement of electrons from one to the other. Now, if electrons are going from, let's say we've got electrons are going to appear on the rod over here, that we're taking electrons away from this clothing, well then the clothing overall, weirdly, is going to seem like it's covered with positive charges. We know it's not really, but if you've stolen all of the electrons, what's going to be left behind is going to be your positive charges. Okay, so if I think we've got some lovely animations here of this rod stabbing someone. So this is them rubbing the rod on a bit of clothing. Okay, enough of that. And now, if we were to bring together two positively charged rods, which are both covered, well, I guess, with both missing electrons, because the positive charges can't move, then if we bring together the two positives, well, similar charges repel and opposites attract. So what's going to happen? That other rod is going to move away. Okay, if you bring together two opposite charges, well then they are going to attract each other. So it's a bit like magnets with north and south, opposites attract. Okay, so a little bit about circuits then. So we're going to start off with a series circuit, and back one. So we're going to start off with a series circuit. Now, what do we need to know about series circuits? Okay, so series circuits is an all or nothing circuit, and take apart the circuit, the rest of the components stop working. Now this circuit here, I've just drawn with 3 resistors in series, and we've got an ammeter, which measures the current. Okay, we've got a voltmeter here to measure the voltage. We've got a resistance in each of the resistors. Now don't forget what resistance means. Resistance is anything that slows down the flow of current. So the bigger the resistance, so when the resistance gets really big, your current is going to get smaller. Okay, so don't forget that resistance is anything that slows down the current. Now, what is current? Current is the flow of charge. Okay, so it's the flow of electrons around the circuit. And what is voltage? Well, voltage is the energy provided by the electrons, or some people call it the driving force behind the circuit. Okay, so a few facts that we need to know about series circuits. Okay, the first one is, let's get a bit of a different color going here. So the first one is resistors in series. Resistors add up. Okay, so if you've got 3 resistors in series and they've all got the same resistance, their resistors add together. If you've got 3 little along here, and each one is worth 2 volts, you just add them all up and that would be a 6 volt. Okay, so voltages add up, resistors add up. And now let's have a look at, let's say that we were asked to calculate the resistance in a component, or to maybe possible 6 marker might be to build a circuit to work out the resistance in a component. So let's draw ourselves a little circuit, and let's say we had some mystery component down here. I'm just going to draw it as a resistor for now. Now let's say we wanted to find out the resistance in this component here. Well, we'd need to do 2 things. If we're going to use this equation to work out resistance, the question might give it to us if we're foundation. It might rearrange it already for us. It might give us R equals V over I. Okay, if I wanted to work out the resistance of this, I need to firstly take the voltmeter reading across that. So voltmeters must be in parallel. Okay, so they measure the difference in the energy being provided by the electrons. So they're in parallel there. And we're going to put our ammeter in series. So that's really important that you know that ammeters are in series, as in they're kind of holding hands with the other components. Voltmeters are in parallel, which means they kind of measure across the component there. Okay, so in this example down here, if we wanted to work out the resistance of a mystery object, we would need to set up the circuit like this. We would need to turn on the power, and we would then measure our ammeter reading. That would give us I, our current, and that voltmeter would give us V, our voltage, and then we can put that into the equation. Now, should the question ask you to be changing the voltage, we can use this symbol down here. That there is a variable resistor. And all that does is it varies the resistance in the circuit. That changes the kind of current and voltage going through it. So over here on this part of the circuit, we could fit in our variable resistor, pop that in there, and have our line through it like so. Okay, we could put our variable resistor in there, and if we wanted to turn it into a method for an experiment to investigate how the current and voltage change in a component, we could use this to adjust the voltage, and just increase the voltage, take the readings, increase the voltage, take the readings, increase the voltage, take the readings. Okay, maybe using an independent variable of changing the voltage or the current, depending what the question says. Okay. Now, a couple of other things about series circuits. Let's just wipe all of this off. And how does current and voltage behave in this type of circuit? Okay, so I said that current is the flow of electrons. The electrons have only got one route to take. So all of the current, let's say we've got, I don't know, 12 amps going past the battery there, 12 amps past the ammeter. You're going to have 12 amps going past this. You're going to have 12 amps going past that. Current is the same all the way around, because all of those electrons have to go past every part of the circuit. Okay, voltage, that's slightly different in this type of circuit. So voltage will have to get shared. So let's say we've got a 6 volt battery. voltage is going to get used up or is going to get kind of split between the resistors here. So if we've got 3 resistors, we're going to have a voltage across each one of 2 here. And that's because energy is being delivered by the electrons, because the electrons are carrying energy and they're delivering some energy to each resistor. So the energy, or the amount of energy being provided by each bit of charge, is shared. Okay, so a lot of waffle for me to say that in this type of circuit, voltage shared, current is the same all the way around. Okay, voltage provided by the battery gets shared, current provided by the battery is the same all the way around. Okay, let's have a quick look then at parallel circuits. Now the good news is that this is basically the opposite of series circuits. Okay, so if you learn one of them, you've learned the other. So in this type of circuit, let's talk about current. Okay, now we've got 2 paths around this circuit. We've got path 1 goes that way. Okay, we'll go back to the battery. Or we've got path 2. It's worth putting that in a different color. Okay, or we've got path 2, which will go around here. Okay, back up here. So if we've got 2 paths, it means that there are 2 choices, 2 options. So actually the current is going to split, because current is the flow of electrons. So current splits down branches. The amount of energy carried by the electrons, voltage is the same down each branch. Give me some numbers if you're not sure about what that means. So let's just wipe out this over here. Okay, so just getting rid of some of that. So if we've got, let's say, use the same numbers as last time, we've got a 12 amp and 6 volt, 12 amps and 6 volts being provided by the batteries there. So current splits down the branches. If these 2 bulbs are identical, you're going to have 6 amps coming down here, because half of the electrons will go this way, and you're going to have 6 amps coming down here, again, because half of the electrons go down this way. Voltage, though, voltage is going to be the same. Every electron that goes past this bulb will be carrying the same amount of energy as it was past the battery. So we're going to have 6 volts and 6 volts there again. Okay, now this type of circuit is not described as an all or nothing circuit. This type of circuit, if a bulb breaks, the other one will keep working. So if that stops working, all of the current then will come down here. We would have 12 amps down here, and that bulb would stay lit just as bright, and it would keep working. Okay, so on to a couple of circuit symbols and us understanding or knowing about LDRs and thermistors. So LDRs and thermistors are quite straightforward. They might sound a bit confusing to start off with, but they're quite straightforward, and I hope they are now for you. So what is an LDR? It's a light-dependent resistor. You need to know a use of it. Well, street lights is a really obvious use of it. When it gets dark, it detects that the light has changed, and it's changing the circuit, so the lights come on. Thermistor is a temperature-dependent resistor. So this detects dependent. It detects a change in temperature that will change the current in the circuit and make something either turn on or turn off. So really great examples of that are ovens, fridges, kettles, thermostats, anything that will turn on or off when it gets too hot or cold. Now, what you do need to know about these is how the changing level of light or the changing temperature affects the resistance. So if we just draw ourselves a quick wonky graph, maybe I can do better than that. Okay, so we draw ourselves some axes there, and if we look at the shape of the graph is the same each time. So I'm going to draw over here, we've got either light for an LDR or temperature for a thermistor, and up here we're going to have resistance. So I'm just going to show on it's a resistance, and that's measured in ohms. So it's the same pattern. Now what this tells us is as light goes up, resistance goes down. Okay, for a thermistor, as temperature goes up, resistance goes down. Okay, now I've seen them, if they come up in 6-mark questions, you can draw a graph. You know, there's just one graph, you draw 2 axes, you draw a curving line, you label it with your resistance and your light. You can even switch around the axes. So if you get an opportunity, draw those little graphs if they ask you about anything to do with it. And you never know, you can get marks. So draw the graphs and then try to explain it as well. As light goes up or temperature goes up, the resistance goes down. Okay, a couple of other things we might want to know. So a diode, we're going to have a closer look at a diode in just a second, but a diode controls the flow of electricity in the circuit. So in this case, it only lets the electrons go through in the forward direction. It won't let them go backwards, which we're going to see a use for that in just a second. An LED is just a kind of cheaper and more energy efficient version of a bulb. It's a light emitting diode, and it means that it gives out light. So look at these arrows that are coming out here. That means it's giving out light. And these arrows going in here means that this is detecting light. So that's a useful little kind of way of remembering them. Okay, so you have to, don't be scared by these graphs. All you have to do is to be able to recognize them and you know, maybe identify them as to what they represent. So this here is a current and voltage graph. Now don't forget that because V equals I times R, the steepness of this line just tells us the resistance. Actually a really flat part of the line means it's got high resistance. So it's really just telling us about how the resistance works. So this type of graph here is for a normal resistor. Okay, so that might have a circuit symbol of a rectangle, 2 lines coming out. So our resistor, which you know, might be a 5 ohm resistor. Okay, so this obeys what we call Ohm's law. Okay, this resistor here obeys Ohm's law. How do we know it obeys Ohm's law? Because it is directly proportional. Okay, and Ohm's law says that current is directly proportional to voltage. That current is directly proportional to voltage under a constant temperature. So it's directly proportional. So I'm trying to think and write at the same time, which is quite difficult. You'll know that if I've told you. So directly proportional, and it goes through 0, 0. It's a straight line, and this tells us that the temperature of this doesn't change. So Ohm's law is that the current and the voltage are directly proportional under a constant temperature. Now, because of that bit about the constant temperature, that helps us to work out the science behind this. I'm going into higher level detail here, I know a little bit with it, but just be prepared to name the type of component that these graphs represent if you're doing foundations here. So this type of graph here, this is for a bulb. Why doesn't this follow Ohm's law? Well, at low temperatures it does, but the bulb heats up. So the directly proportional bit would have the line carrying on like that, but the bulb heats up, it gets hot. So when it gets hot, it gets a really high resistance. So it doesn't follow, so this doesn't follow Ohm's law. Why? Because its temperature is changing. Okay, now this little chestnut over here, this is our diode. So the diode, job of the diode is to only let electricity through in one direction, and that is exactly what it's doing here. So current and voltage are only flowing in the positive direction here. There is no current or voltage if we try to reverse the current. Okay, so a diode there is controlling the flow of electrons. Okay, and again, obviously doesn't follow Ohm's law because they're not directly proportional. Okay, so we've got diode, we've got bulb, we've got resistor. Okay, so a little bit onto electricity in the home. So AC versus DC. AC is mains electricity, so your TV and your fridge will operate from AC. AC means alternating current, and if we look at the current here on this graph, alternating current just means it's going backwards, then forwards, then backwards, then forwards again. Okay, it's literally switching direction in the positive and negative direction. Now, so DC means direct current, and that is electricity that just goes in one direction. Now, to turn, you may not need to know this, but it might be useful for higher tier, is if to turn AC into DC, you use a diode. And that's what we've already seen. You'd use your diode. Why? because it controls the flow of, it controls the direction of the current. Okay, so if you fit a diode, then it's only letting the electricity flow through in one direction. So you'll get a straight line on this graph here showing the voltage changing over time. If you were asked to show to calculate maybe the time period of this wave, you know, they'll tell you what each division is worth on the screen there. You look at one complete wave. One complete wave will finish here. So what have we got there? We've got 4 squares. Okay, and we know each time division is that, so you do 4 times 0.05, and that'll tell you the time period of one wave, so how long it takes for the wave to go backwards and forwards. Okay. Okay, so wiring plugs and a bit of domestic safety for electricity. So let's get the colors of the wires up here, and that's going to remind us where they go in the plug. So we've got striped, we've got blue, we have got over here brown. So second letter tells you where they go. Blue wire goes on the left, brown on the right, striped at the top. So live wire is the one with the fuse on it. Now inside the fuse is a thin little piece of wire. If the current gets too high, the little wire inside gets hot and melts. If it melts, it breaks the circuit, stops the flow of current, no one dies, which is always good. Neutral wire is going to be carrying electricity from your fridge or from your appliance back to the power station. Now that's why, because voltage gets used up in a series circuit, the neutral wire should normally have a voltage in it of 0 volts. Because don't forget, your live wire is carrying your voltage of 230 volts in the house, and that'll be carrying alternating current. And that alternating current operates at 50 hertz, so that's 50 times a second. It flips backwards and forwards for our, you know, our mains electricity out of our plug sockets. So our neutral wire will be carrying 0 volts. Earth wire we're going to look at in a minute, but earth wire is to protect you from electrocution should your live wire come loose. Okay, structure of the plug, how this is designed to work well. We've got plastic on the outer insulation, that's to prevent electrocution because it's an insulator. We've got brass pins because they're really strong. You don't want to trip on your cable and all the live wire to come loose and hurt someone. So we've got brass pins because they're good conductors of electricity and they're strong. Okay, so a little bit of electrical safety. Now, an important thing to remember is it's current that kills. So when talking about electricity and dangers of electricity, make sure you're talking about current and not voltage. Current kills. So overloaded plug sockets draws too much current, which can cause a fire or it can cause electrocution. Okay, having frayed wires means that current could flow through an individual that touches them, and that could kill them. Okay, so the frayed wires are here where the live wires are exposed. So we can also work out what type of fuse should go in an appliance from this equation: P equals I times V. So the question would tell you the power rating of an appliance. So maybe it's a 2000 watt hi-fi system. That'd be very powerful. And then it tells, we know the voltage because the voltage is 230 volts. Okay, so we could rearrange the equation. Again, foundation tier won't have to do this, but P over V, okay, to work out the current reading of the device. So quickly on a calculator, 2000 divided by 230 gives us an answer of 8.7. So 8.7 amps is what goes through the appliance. Well, I have to use the fuse rating above that. So you're going to have to choose a fuse which is higher than 8.7. So that means I'm going to have to go for a 13 amp fuse. Okay, and they'll tell you the fuses in the question about what's available, but that's how to work that out. Okay, so the earth wire in an appliance, what's the earth wire for? The earth wire is there should the live wire, which is carrying your current and your 230 volts, if your live wire comes loose and touches the metal appliance here, so your live wire goes and touches that metal case, look at him, he's foolishly got his hand on an electric cooker which has got metal on the outside, he is going to catch on fire and electrocute himself. So the earth wire, if you see down here, is already connected to the metal case. So the electricity, instead of flowing through our poor victim here, the electricity is going to flow through the earth back down into the ground. Now it'll flow through the earth back down the cable, and then somewhere in your house that cable will be attached to the ground, so that the actual ground, so that the electricity can flow back to the earth where it wants to go. Okay, an RCCB, residual current circuit breaker. It's a bit like a fuse. If the current is too high, an electromagnet pulls a switch. So if the current gets too high, an electromagnet just pulls out a kind of metal bolt, and that will break the circuit. Why is it better? Well, it's a bit faster than a fuse, so it might protect you a little bit more. It's a little bit cheaper because you don't have to replace your fuse. So those are both good reasons. And I'm sure you've probably got one of these. I mean, they're called a fuse box in the house because we use old language from days gone by, but really they're a residual current circuit breaker. If they've got switches on, you can just flick the switch back down. Okay, so on to a bit of atomic physics then. So the last maybe third or quarter of our topic. So what you might need to do is to compare the plum pudding model and the nuclear model. We've got the two pictures of them here. So they'll more than likely they'll give you pictures of them both. So in the plum pudding model, we've got this kind of like dough of positive charge. There's no protons. It's just this kind of pudding, this sponge, if you like, in the cake that is has a positive charge, but embedded in that we do have electrons. The electrons don't move around, they're fixed. Okay, and this whole plum pudding will be the kind of the same size as the whole of the nuclear model. Oh, I need to stop doing that. So so comparing the positions then, the electrons are embedded here, they're fixed in places. Here the electrons are free to orbit the atom, they move at a distance away from the atom. Okay, there are no neutrons in the plum pudding model. I'm doing it again. The nucleus has got neutrons in here, so there are protons and neutrons that are in a really small concentrated mass. Okay, so most of the atom, they found out from the Rutherford and Marsden scattering experiment, the experiment where they fired alpha particles at a thin layer of gold leaf. They fired those alpha particles in, most went straight through, but a tiny number bounced back again. Those tiny number bounced back again because there was a really small positively charged nucleus. So only those electrons, only those alpha particles that bounce right into the middle of the nucleus, they're the ones that come back again. Okay, and it's a tiny number. Okay, so nuclear model has got a positively charged concentrated mass in the middle, and that's what this Rutherford and Marsden experiment found out, and that's why they could get rid of their plum pudding model and swap it with this much better nuclear model. Okay, so a little bit on radioactivity then, last 10 minutes, and let's have a little look at how we how atoms become radioactive. Okay, so we need to know what an isotope is. Here we've got 3 isotopes of carbon, and each isotope has got a different mass number. Each one would have a proton number or atomic number of 6, because they've all got 6 protons in the middle. So this number, the mass number, tells us they've got different numbers of neutrons. So the definition of an isotope is it's a version of an atom with a different number of neutrons. Now, some of these, if they've got a lot of neutrons, they become unstable. Okay, if they're unstable, they can release radiation. Okay, if they released radiation, it's either going to be alpha, beta, or gamma. Okay, which we're about to have a look at now. Oh, just before we do that, background radiation. So background radiation, there is a little bit of radiation all around us right now. Only 13% of it is man-made, mostly from natural sources. So radon gas from granite is where most of our background radiation comes from. Man-made sources are hospitals, nuclear power stations, and we can see that actually where you live in the country has a big factor on how much radiation you get. So places where there's lots of granite, there's high levels of radon gas, so you're more likely to have maybe a high dose of radiation. Okay, and jobs can affect it as well. So if you're someone that works in the nuclear industry, someone that works in a hospital with nuclear radiation, someone who works in an airplane, because you're closer to the top of the atmosphere, pilots and airline stewards tend to have higher levels of radiation in them because they're high up in the sky, and so they receive more gamma rays from outer space. People that go up in a space station tend to have high levels of radiation in them. So around us all the time is this background radiation. Now, radiation comes in three forms: alpha, beta, and gamma. Okay, so alpha, what is an alpha particle? It's 2 protons, 2 neutrons, or it is a helium nucleus. What is beta radiation? It's a high energy electron from the nucleus. What is gamma radiation? Well, it's just a wave of electromagnetic energy, a really high frequency wave of electromagnetic radiation. Now, for higher tier, you need to know how it's deflected by a magnetic field. So because alpha and beta have got charges, they've got positive or negative charges, they will get deflected in a magnetic field. Gamma rays won't, they'll go straight through. Now, what most people are really happy with alpha, beta, gamma is what they get stopped by. So alpha, stopped by paper. Okay, beta will go a few more centimeters in air, will get stopped by thin aluminium, and gamma rays will only get stopped by really thick lead or meters and meters of concrete. So why are they dangerous, these things then? So alpha radiation is highly ionizing. Ionizing means to strip electrons. Okay, because they've got a 2+ charge, because there's 2 protons in there, they will strip electrons. Now that's really bad if that happens to your DNA inside your cells. Beta radiation is is reasonably ionizing, and gamma radiation is a little bit ionizing. The reason why gamma radiation is more likely to hurt us is because it can go straight through us, and so it will penetrate us really easily. Alpha radiation won't get into us because it's stopped by paper. So alpha radiation on the outside is quite safe, but on the inside it's really dangerous because it's really ionizing. And beta radiation again is moderately, it's kind of in between the two. So it's reasonably ionizing, it's reasonably penetrating, and so it is quite dangerous on the inside and on the outside. Okay, so uses of radiation then. This could be a possible 6 marker. Alpha radiation is used in a smoke detector. So there is a emitter and a detector, and all they do is the emitter sends out these little particles of alpha radiation, and the detector detects them. As long as it's detecting them, the alarm doesn't go off. If a little glob of smoke comes up there and a little blob of smoke appears, well, it's going to block the flow of those alpha particles and it's going to set the alarm off. A really similar thing happens here. You've got an emitter underneath this could be a tinfoil factory or it could be a paper factory. You're going to have an emitter and a detector on both sides. Okay, and it's going to detect the amount of radiation that goes through, because there will be a little flow of them. And if the amount of radiation going through changes, they know that the tinfoil or paper has got thicker or thinner than it was, so they can adjust these huge rollers that are squeezing it as it goes through. So it's our beta radiation. Gamma radiation, chemotherapy, treating cancers, sterilizing medical equipment, because it kills all cells. Okay, that's the reason why we use gamma radiation for cancer treatment or sterilizing medical equipment, because it kills all cells. Okay, so half-life then, this measure of half-life. What is half-life? Half-life is the average time taken for the number of nuclei in a sample to go down by half, or the time taken for the counts per second, the number of emissions per second to go down by half. Okay, so a skill that you might need to know is from a graph like this, which plots the count rate, or the number of atoms, radioactive atoms, how do we work out the half-life of this? All you have to do is look at where it starts. Okay, go down to half that number, half-life, go down to half that number, go across until you hit the line and come down. And that will tell you that our half-life for this sample is 6 days. Every 6 days that the number of counts goes down by half. We could even do it again, get half that number there, come down again, and we've got the same time distance between each half-life. Again, if you've got 20 there, I bet that if you draw a line along here, we go all the way to 24, and that being, nope, 18, and that being the half-life again. Okay, possible thing you might have to do is you might be asked to work out if a sample has got maybe 240 atoms, radioactive atoms at the start. After 6 hours, there are 60 left. Okay, so you start off with 240 radioactive atoms at the start. After 6 hours, there's only 60 left. How many half-lives has it gone through? So just halve it each time, and that'll be one half-life. So from 240, if we halve that once, we get 120. So that's one half-life. And then we halve it again down to 60. That's our second half-life. So the answer is that it's gone through 2 half-lives in 6 hours. So if it's gone through 2 half-lives in 6 hours, one half-life must be 3 hours long. Okay, you guys are doing really well. I'm flagging, but we've got just a little bit left, not long at all. We might overrun by a minute or two, I hope you don't mind. So nuclear fission versus nuclear fusion. So what's the difference between these two things? Okay, the clue, don't forget, is in the name. To fuse means to join together. To fuse means to join together. So the fusion is the joining of small atoms. Fission is the splitting of large atoms. Okay, so fusion is them joining together. Now they both, this is quite important, they both release huge amounts of energy. That's why we can use fission in a nuclear bomb or a nuclear reactor, is because they release so much energy. And that also explains why we can feel the heat from the sun millions of miles away, because of the huge amount of energy that's released from it. So fusion happens in stars, fission happens in bombs and nuclear reactors. Okay, so how does fission work? Fission, a neutron will be absorbed into, in fact, we've got fission up here. So a neutron will go into a uranium atom, and that uranium, you can see there, the mass number changes, it gets heavier. And because it's heavier, it's unstable, and so it's going to split up. And when it splits, huge amount of energy released and more neutrons. Now, what a skill you might get asked to demonstrate is to kind of complete this diagram. So pick one of the neutrons and let that hit into an atom of uranium. That atom of uranium will then, so that could be the 235. This one will turn into the 236 uranium. And all we're doing is just repeating this diagram again. That then is going to split into an atom of Kr and Ba. And again, you're going to get 3 more neutrons. Okay, so you might be asked to complete a chain reaction. You could do the same thing again up here, okay, and just splitting it off exactly. You're just repeating the diagram above it, just to show that this is a chain reaction, that the neutrons that come out of one reaction then go on to start off other reactions as well. Okay, and don't often see questions about fission and fusion, but those really are, that's everything you need to know. So star lifetime, so evolution of a star. So the names of the stages, I think everyone that I've ever practiced it with seems pretty happy with this. So all stars start off as a protostar. The protostar, just like a prototype, is your first star, your little baby star. Now, we do need to know the names of the forces that make these, that make the stars. So we've got the inner force of gravity. So gravity is pointing into the star. That's going to be bits and pieces are going to fall into the star, so dust and gas. And then we've got the outward force of outward pressure fusion. So fusion is what happens in the star. So the star has got an outward pressure of fusion, and that should be balanced by the inward force of gravity. So if I draw our star there, you've got the outward force of fusion, or pressure from fusion, you've got the inward force of gravity. Now, if the star is staying the same size, it's not changing size, the forces must be balanced. If the star is expanding, the outward forces must be bigger. If the star is contracting, the inward forces must be bigger. So our stage is here. Now the difference between, so all stars start off as a protostar. They all go main sequence, and our star is a main sequence star at the moment. Now the lightest stars, like our sun, is going to go, so I mean light in mass, as in like not very heavy. So they're going to go red giant, white dwarf, black dwarf. It's just going to kind of cool down, and it's going to contract into a white dwarf and contract again into a black dwarf. Now the heaviest ones, the heaviest stars, are going to expand into a red supergiant, because they're so heavy, they're super. That's going to explode then in a supernova. And when it explodes in a supernova, that's where your really heavy elements are created. So your elements heavier than iron are created in a supernova. Now for the kind of the medium stars, so heavier than these ones over on the light side, but heavier than those, they're going to turn into a neutron star. And if they're really heavy, they're going to go from a neutron star and collapse into a black hole. Only thing you need to know about a black hole is light cannot escape it. Okay, so what else might we need to know? When the star first lights up, that's when it starts fusion. It's turning its most common fuels are hydrogen and helium. It's using those fuels up in fusion. Once they start to use those fuels up, it starts to expand into a red supergiant, using up heavier elements all the way up to iron. And then when it goes supernova, your really heavy elements are going to be formed. So your gold that maybe your parents have on their wedding ring is going to be have been created in a supernova somewhere, which is quite a nice thought. Okay, ladies and gentlemen, I think I've talked for long enough. All I want to say is best of luck to you. I know you've worked really hard this year. It's been a pleasure teaching you. And I hope you take some of your confidence into the exam tomorrow. Make sure you have a good meal. Enjoy it. I know that sounds really difficult to enjoy the exam, but do enjoy it. Smile at the start of the exam. Relax. If you can't remember something straight away, leave it, and it'll pop back into your head when you least expect it. Okay, so the more you squeeze your brain to try and get information out, the more it resists. Okay, so just relax. Take it easy, enjoy what you're doing, do a bit of brain dumping as well in your paper if you want. Okay, jot some information down when you have it to hand, so in case you later forget it. And ladies and gentlemen, thank you very much, and good night.